So hi, today I'm going to talk about optimizing Bayesian information revelation strategy in prediction market, the Alice Bob Alice case. Sorry, it's another long title, and this is joint work with Grant and Beck. Okay, so what is prediction market? So prediction market provide a compelling and unique way to sell the information and aggregate the information. So here is the example, is a football game. So if there is a game between Michigan and Ohio State, so there are two kinds of shares, one the yes share and no share. So if Michigan wins in the end, the yes share gonna value $1 and no share value nothing. If Ohio wins, then the opposite thing gonna happen. So if you really believe Michigan gonna win, so you think the value of the yes share gonna close to $1. And currently the price is 65 cents. So in this case, you're gonna buy the yes share until it increases to your own belief. So that is what I mean, the buy low, sell high. And that is how people interact with the market to review their information. Okay. And then we're gonna ask how can we maximize our expected payment by reviewing our information? When, how to review it? Should we review it immediately or should we review it later? Should we review it gradually, step by step, or maybe we can just review it everything at one time? Okay, so let's still see the football game example. So if everyone is watching the TV and there is a touchdown there, and definitely you should review your information immediately, because if you review it later, then other people are going to review it. It's then your information is going to become meaningless. So it seems like everyone wants to sell their information, but if everyone has the same information, then you must be the first guy. And let's see a tricky case. If Alice is one player's wife and she happens to know a secret information that is her husband is injured and other people do not know this. So this is going to be a complicated case for Alice. Should she review it later or should she do some spoofing thing, lying in her Twitter, and should she gradually review it without spoofing? And this talk, we focus on the third part. It's that is why we call it Bayesian, because we borrow the concept from the Bayesian persuasion. So we assume Alice commits the information revolution rule. It's at the beginning, and then Alice gonna follow that rule. So there's no spoofing there. But we admit that there is an interesting future direction. It's we're considering the spoofing case, but it doesn't cover in our paper and this talk. Okay, so this is the outline. Okay, we're gonna first talk about the Alice game, and then show our results, and then show how to obtain it. Okay. So this game is actually proposed by Chen and several people in 2007, 2010, and it's studied by Chen and Wagner in 2016. So it's a simple game. It's the simplest game that we can analyze the strategy there. So Alice participated in the market first by maybe reviewing some of her information. And then Bob only has one chance to participate in the market. And then Alice participated again. So we want to analyze what is Alice's optimal information revolution strategy. And the prior were analyzed to edge cases. So one is when Alice's information, Bob's information are conditional independent. They prove that it's actually the substitute case. It's like the touchdown thing. So your information overlap a lot with other people's information. In this case, you should participate in the market as soon as possible. And for the independent case, they show that it implies the complements. So your information is actually a complement with other people. So you should wait until other people reveal their information, and then your information can become more valuable if you review it later. So then one natural question is, how about the general information structure? And that is our work. So surprisingly, we show that even if Alice's private information is 1 bit, Still, in some situation, the optimal information resolution strategy for Alice is reveal partial information for the first stage and then reveal everything in the last stage. And also we show this, what we call revolution principle. It's like it is enough for Alice to pick her non-signal space as her private information space. So maybe computing the optimal strategy is complicated, but it's not that complicated because we don't need to consider like if Alice has a very complicated non-signal space. And based on this result, we provide F-pitas when Alice information is come from a constant size set. So prior to our work, it's even an open question like whether this optimal information resolution strategy exists, even Alice signal. And this is Alice signaling scheme in the first stage. So Alice commit a transition matrix that is like when my private information is what, then I'm going to use what distribution for my non-signal space. And if it is the identity matrix or like 0, 1, 1, 0 matrix, that means like Alice reviews the full information in the first stage. If it's like this third column, in this case, no matter what is Alice's private signal, she always uses the same distribution for the non-signal space. So like her non-signal will not reveal anything about her private signal because she always does the same thing. And for the middle part, it's like sometimes I tell the truth, sometimes I play some mixed strategy there. So that is the partial information. And we have this experiment result when Alice's private information is binary. It's like for some situation, actually the prior work has already shown, like in the substitutes and complements situation, Alice's best strategy is review no information, full information. And we show is like for some information structure that is in between, Alice's optimal strategy is review this partial information. Okay. Now let's see how can we get this result. Okay, so I think I'm gonna omit the introduction of the probability scoring rule and market scoring rule. So let's just use this to see the prediction market. That may not is the analysis, but gonna give us a better view for this problem. So basically, like the prediction market provides a way for people to sell their information. So for the trader, he has information X, and then the market gonna pay him the value of this information. So what does the value of the information mean? So when the information comes, more and more information comes, actually the uncertainty of the predicted result gonna decrease. So we actually pay people the reduction of this uncertainty, or we call entropy here. And so if the information X actually just tell you what is the result, and then the uncertainty gonna decrease to 0. So that is the most valuable information. But if it's like independent with the result, and then the uncertainty of the result will not change. And you can also understand it as the correlation between the information and the predicted result, conditioning on the knowing information. And still, if they are independent, the correlation is going to be 0. If they are very highly correlated, then the information X is very valuable. Okay. And then let's go back to the Alice scheme with commitment. So basically, for this scheme, in the first stage, Alice is going to be paid by the value of her non-signal X sigma. And in the second stage, Bob is going to be paid by his private information's value, conditioning on Alice's non-signal. And in the last stage, if Alice can learn Bob's information from Bob's trading behavior, and then still there is still some information monotonicity here. Definitely, if you review more information, the more value is going to be paid. So in the last stage, Alice is going to review everything. And in this case, the sum of the payment is actually the value of the all private information, and it's actually very natural to obtain this result. It's very similar with the chain rule. Okay. So then how we optimize Alice's effective payment? So since if Alice can learn Bob's information, then it's just a constant sum game. So what Alice should do is minimize Bob's effective payment. So basically, Alice should pick proper transition matrix M such that the value of Bob's private information is minimized, conditioning on this MXA. And the problem is, like, sometimes Alice cannot learn Bob's information from Bob's trading behavior. But luckily, we will show that you can still tune the transition matrix a little bit, such that you can always learn Bob's information from Bob's trading behavior, and still you only sacrifice a little bit. So basically, that is 2 steps. So let's see the example why we can tune the transition matrix a little bit. Let's go to this XOR example. If Alice and Bob, both of them have a binary signal, and the final result is the XOR of their binary signal, and also their binary signal are independent with each other. So in this case, if Alice review like nothing, and then Bob know nothing about the final result. But if Alice review like a little bit thing, then Bob gonna know something. So basically, if Alice just want to minimize the value of Bob's information, Alice should review nothing in the first stage. But the problem is like, it will not give Bob any motivation to participate in the market. And if Bob doesn't participate in the market, then Alice cannot learn anything about Bob's information. But if Alice do this sacrifice a little bit, like review the information with probability epsilon, and with y minus epsilon review a random result. Like in this case, we will show like what Alice loses is actually very small, but from this, Alice can entice Bob to participate in the market and learn everything. So that is the second step. So we don't need to worry about Alice cannot learn Bob's information. So we should only focus on the first step, is this like how to minimize Bob's expected payment. One thing is like I don't know, for me it's not very intuitive because like I always think the conditional symbol as a minus symbol. So it seems like the value of Bob's information is kind of his private information's value minus what Alice reviewed at the beginning. So I'm gonna think like maybe it's a decreasing function of this transition matrix. Here, I mean decreasing function is like from no information to full information. But like Prior has already shown that it's actually no, causing the XOR case like what we mentioned. It's possible like conditioning on XA, the value of Bob's private information is greater than no XA. And then we're gonna ask like, is that possible? Like this is actually a monotone function of M. Like given the information structure, this is actually a monotone function of M. It's sometimes increasing, sometimes decreasing. But like the experimental result we showed before, the answer is still no. And then it remains how can we do it? So the first principle we want to show is like, it's enough to optimizing over only the square matrices. And also we need to show its continuous. We need to show like if you perturb the M a little bit, still the function is still being perturbed a little bit. Okay. And what we show the revolution principle. Okay, I think. Okay. So we're gonna first show a non-trivial observation of this mu m. Mu m is the expected payment of, if Bob's expected payment, we want to minimize this Bob's expected payment. And it actually turns out to be a very complicated function. It's not linear, it's not convex. But it turns out it satisfies this, what we call the decomposability property. It can be decomposed as the sum of f function of each column. And for the f function is linear for the scalar. So it's not a linear function, but it's linear for the scalar. And then we're gonna show that this observation gonna implies the revolution principle. I think I don't have, do I have time? Okay, so one thing we want to show, one possible like step we can try is like maybe we can show like for every m belong to this like the complicated non-signal space, there exists a square matrix such that they have the same value. But it turns out this statement is actually not true. And also it's because this f function is actually the small f function is very complicated. It's only linear for the scalar. So we cannot prove this result. But it turns out we can prove that it always exists a square matrix such that the value of this square matrix is less than the m, like given any m. So with this property, then we can easily show the revolution principle. And we show this by constructing a linear program and use the fundamental theorem of the linear programming. Any optimal feasible solution implies optimal basic feasible solution. Okay. And the decomposability is also not very, I think I don't have time to cover it, but okay. And the algorithm is also based on the linear programming. Okay, so the future directions I have is like first is a hardness result. So we want to show like when Alice signal space is like arbitrarily large, like can we show like maybe it's like very hard to compute the optimal signal strategy. Another thing is like this spoofing thing. Like if without this commitment power, if Alice can lie for the translation rule, how can we analyze the equilibrium there? And for the one-shot game or for the many round game. And also another thing is like beyond Alice Bob Alice case. Still, like I just hope that information theoretical view of the prediction market can help. Like for this case, because if we think a very simple case, like if Alice is the expert who actually knows the predicted result, and how should she do to maximize her expected payment. So that is not Alice Bob Alice case. That is Alice with all other agents in the prediction market. So with the information theoretical view, we can say that the best strategy for Alice is review everything at the beginning if she is the expert who actually knows the final result. Because no matter what kind of magic strategy she used to participate in the market, only the maximum expected payment for the market is actually the uncertainty of the final result, and Alice can obtain that at the beginning. So that comes from the kind of this information monotonicity of that information theoretical view. And we are working on like try to use this view to analyze like more general case. Okay. Thanks.